Hey everyone, welcome back to the channel Advanced Tech. This is part 4 for our series Windows Kernel Exploitation. Today we are diving into the world of kernel vulnerability, specifically buffer overflow. We are going to cover in kernel space. We'll be breaking down a vulnerable driver example, show how it works and understand how attacker can potentially exploit it. Let's get into it. So first of all, we're gonna discuss about kernel land and user land. In modern operating system, we have two distinct mode of operations: user land and kernel mode. Kernel land or mode, you can ever say whatever you like. Kernel mode is where core system function run, things like interacting with hardware and managing memory. User mode applications like the ones we use every day can't directly access kernel mode object. This separation is important because it protects the system from accidental or malicious modification to the kernel. But how do we interact with the kernel driver from user mode? Yes, that's the main question. So we use handles, and handles act as the intermediaries, allowing user mode application to communicate with the kernel mode driver very safely. So let me show you how to create a handle using create file API. So I have already opened from the documentation, or you can just google it. This file, create file a function, you will definitely land on this page. So here's the handle for create file a. Here we are opening handle to a device driver using the device name, access flag, and some security attributes. If successful, the handle return will allow us to communicate with the driver using another important function called device IO control. Okay, so once we have the handle to our driver, okay, this is the API. So once we have the handle to the driver, we can send IO control code with the help of device IO control API. This is where things get interesting because driver use IRPs, input output request packets, to process the data sent from the user mode. Yep, and this is the code you can see here. Now let's take a look at the heart of this vulnerability, the buffer overflow driver. The bug here is pretty simple but devastating. Okay, this code defines behavior of kernel driver that can trigger based buffer overflow. So here is the code. Okay, you can find it from HAVD driver. Go to Windows and open the buffer overflow file. So I have already opened it. So yeah, here it is. So first of all, we have to include the header file. So hash include buffer overflow.h. I'll explain you all the things inside the code step by step. Okay, this include buffer overflow.h header file, which is likely contains declaration, constant, and macros relevant to this code. Then after that, we have conditional compilation for memory allocation pragma. So here is the pragma code and the definitions. So the section uses a hash pragma alloc text directive to ensure that the function trigger buffer overflow stack and buffer overflow stack IOCTL handler that are paged out when not in use. This is a memory management optimization. The functions are marked for paging to the disk when they are not active, reducing memory usage. Okay, then after that we have this function definition for trigger buffer overflow stack. So here you can see underscore decl spec safe buffers. So this is a Microsoft specific extension that disables some security checks for buffer overflows within this function, possibly for performance reasons or testing. The function triggers buffer overflow accept two parameters only: user buffer pointed to the user buffer size. Size is the size of user mode buffer. This function returns an anti-status code indicating success or failure. Then we have kernel mode buffer initialization. There's a variable to store the status of the function initialized to status success. A kernel mode buffer initialized to 0. The size of this buffer is definitely by buffer size, which would be set in the header which would be set in the header file. Okay guys, so check pageable code. So after that we can see here, this is paste code, right? So this macro ensures that functions can only be called at irql equals to passive level. So it meaning like it's allowed to be paged out and is not called at higher interrupt levels. So yeah, that's it. So verifying if buffer resides in user mode, here is the thing. Okay, try probe read, you can read this. Okay, and actually this starts structure exception handling block, okay, to catch any exception that might occur. Example, invalid memory access. Probe for read, this function verifies that user buffer resides in user mode memory and is accessible for reading. It also checks the size of the buffer and the alignment of the data. Okay, yeah. Then after that we have debugging information. All these dbg print we use to print all that information. Like dbg print calls out print out debugging information, including the addresses and the size of the user mode buffer and the kernel mode buffer. This helps developer to understand the state of memory during the function execution. After that we have if def secure. So this is the secure way of defining RTL copy memory copy memory operation, and this is the insecure way. Okay, so let me tell you what's the secure way is telling here. If code is compiled with secure flag, it securely copies the user buffer into kernel buffer using RTL copy memory. The size passed to RTL copy memory is the size of kernel buffer, ensuring no overflows occur. Okay, if the secure flag is not defined, it copies size bytes from the user buffer to kernel buffer, which can cause stack buffer overflow if size is greater than the size of kernel buffer. Okay, so yep, that's what is happening over here. But in this it's already written in comments. Okay, RTL copy memory mem copy without validating the size, if the size is greater than or equal to the size of the kernel buffer. Okay, so yeah, that's it. Then we have this code. Okay, exceptional handling. So this underscore expect block catches exceptions that may occur during the memory copy operation. If an exception happens, for example, invalid memory access, the execution code is retrieved using get exception code and stored in the status variable. Debug information about the exception is printed. Then we have return status. This is okay. The function returns the anti-status result, either a status success if everything worked correctly, or the exception code is a or the exception code if an error occurred. Okay, then after that we have uh, this buffer overflow stack ioctl handler. Okay, so this function handles ioctl request and calls the trigger buffer overflow function. It takes two parameters. IRP first is pointed to an IO request packet, then IRP IRP SP. This is a pointer to the stack location of the IO request packet, which contain parameter for the operation. The function also returns an anti-status code. Yep. So after that you can see here. Okay, the size is initialized to 0, which will later hold the size of the input buffer. User buffer is initialized to null, which will later point to the buffer provided by the user. Okay, status is initialized to status unsuccessful and will be updated with the result of the buffer overflow function. Okay, So then we have this ignore IRP, like unreferenced parameter IRP. This macro IRP as an unreferenced parameter which surpasses compiler warning since the function does not use the parameter correctly. Okay, so yeah, after that we have this user buffer IRSP parameter. Okay, what does this mean? This the user buffer and the size are extracted from the IO stack location, and this represents the data user is sending through the IOCTL requests. Okay, after that we have we are calling the buffer overflow function. If a user buffer is valid, that is not null, it calls trigger buffer overflow with the user buffer and its size. The result is stored in status. Okay, and return status, it's the function that results in empty status, which indicates whether the operation is succeeded or failed. This code defines stack buffer overflow vulnerability handler in a kernel driver. You can see the secure path ensures no overflow occur by limiting the copy size to the kernel buffer size, while the vulnerable path allows an attacker to pass an arbitrary size, leading to a buffer overflow. If size exceeds the kernel buffer's capacity switches, it will just trigger it. After that, as we have seen this thing, okay, and this we know like this is the secure way of illustrating the size of kernel buffer and user buffer, and this is the insecure way. Okay, to exploit this vulnerability, an attacker can craft specifically designed IO request that passes a buffer larger than the expected size. Using the device IO control function, they can pass an oversized buffer, triggers the overflow, and potentially executing arbitrary code in the kernel. That's what we are going to do now. Okay, let's hit it. First of all, we'll create one file. Now we'll explore how to use IDA to analyze the have driver, specifically focusing on how functions in the driver lead to kernel exploitation and stuff like that. And we'll dissect the key functions, including buffer overflow and related vulnerabilities as well. So first of all, we need to go in our Windows operating system. We need to load the file in IDA. We can do this like this, don't save. Okay, open, just double click on this, and yeah, okay, it will load this file. Okay, so in this one you can sort it by function name. Okay, yeah, and this will be easy to find the required function. Okay, so yeah, to begin with, our goal is to find is like to find IRP device IOCTL handler function, which is responsible for handling input output controls request. So inside this function we will definitely identify various vulnerable operation, including stack buffer overflow, and there are more arbitrary write IOCTL handler, buffer overflow, stack IOCTL handler, something like that. So first let's hunt for IRP device control CTL handler. Okay, first let's change it to text, please. Okay, I think yeah, that's pretty cool. So just click on it, and yeah, here you can see there are we have loaded this, and you can see we have free UAF object, non-paged handler, use UAF object pool. There are so much stuff over here, these are all vulnerable functions, and for for different techniques, illustrating different techniques. So we are going to explore here buffer overflow stack IOCTL handler. You can see this function. Okay, you can just go here and see what's happening behind the back. So here sub rsp 28h. Okay, it means this adjusts the stack pointer and reserving space for the local variable. Then we have move irp plus 20. We have seen this thing while doing the code analysis over here. Okay, so this is the part. Okay, so this is so we are basically seeing the assembly of the high level code. So this is how it goes. So yeah, so this move irp plus 20h. This instruction fetches the user buffer from the IO request packet irp, which is a structure used to send requests to device drivers. Then we have move eax 0c something 1h. This sets the return value status to failure code status as unsuccessful in case of something goes wrong, like in exception handling. So after that we have move edx irpsp plus 10h. It retrieves the size of the input buffer from the irp. Okay, so next we have test irp comma irp. This test if the user buffer is valid. If it's null, execution jumps to location this location. Okay, so yeah, and after that we have call trigger buffer overflow stack. This is where the vulnerable function is. Okay, and we need to check this out as well. So let's analyze what this function is. We'll double click it and we can see there are a lot of instructions. So let's break it down one by one. Okay, so we'll see this from here. Okay, sub uh, rsp 820h, because these are just normal parameters like uh, rbx rsp plus there's a first there's a one argument here, okay, from rbx which is moving to rsp, like that. But the magic is going on here. Okay, so we have sub rsp 820h. It reserves more stack space for the kernel buffer. Okay, and this is the actual which is located for for the buffer inside kernel. So then after that we have move rsi comma size. It moves the size of the user buffer into the rsi register. Then we have move rdi user buffer. It moves the pointer to the user buffer into the rdi register. Then we have lea user buffer rsp plus 838h plus kernel buffer. So this line loads the address of the kernel buffer into the user buffer. And at last we can see the call mem set. This clears out the kernel buffer by filling it with zeros. The vulnerability lies in the absence of proper bounds checking of a user buffer and size, which can result in a buffer overflow if the user supplied size exceeds the size of kernel buffer. Going back to IOCTL handler, okay, so we can just go back from here and we can yeah, we are now on this part. Okay, again, now we just need to check. Okay, where the first first jump happens, where it's going to this function. So how we can do it? We just need to click on this and we can backtrace this function. We can go here and we can see there's a move ecx r9d, and then we have sub ecx, and there is something, and after that jz location, something like that. So this means like move ECXR90. It loads the IOCTL code into the ECX, and then what we have in sub instruction, it compares the IOCTL code to a predefined value, which is like 222003H, and which correspond to the buffer overflow stack IOCTL handler. Then it if the comparison matches with ECX equals to the above value, which is this, okay, execution jumps to the handler for the buffer overflow vulnerability. Yeah. So if enough of this theory, so now we'll create one exploit which will give us the blue screen of death if run on the same system. So yeah, we'll open Kali. We'll write this exploit over here. Okay, and now let's start building our exploit. So we'll trigger the blue screen of that. For right, we'll write this program in Python. In this have you can see exploit written in C, but for learning sake, you can use Python or any other programming language you are comfortable with. But it should contain operating system library for Windows as well, and the C types that we're gonna use. So yeah, I think now we'll use the Visual Studio Code to write our code. So I'll write my exploit over here. So first of all, now we are going to import struct, then import sys. After that, operating system from C types. We need everything, put everything. Then after that, we are going to load kernel 32.dll. Kernel 32 equals to, this will be the DLL, contains all the DLLs, APIs 32. We need this specific one. After that, we need to get a handle to the one driver. Okay, so if it's small, I'll make it large. Okay, I hope this is visible to you guys. Okay, so if I'm not loud, okay, so just comment below. I'll use mic next time. I do have mic, but I don't use it usually. I don't need that. So yeah, so after that we need to create handle. Okay, handle equals to kernel 32 dot dll, oh sorry, kernel 32 dot, we need create file API file a. Okay, inside that we need driver path in bytes, so we'll give b first, then 1 2 3 4. Okay, dot 1 2, and the path of hack sys extreme vulnerable driver. Okay, comma, driver path has bytes. I'll mention this in our comments. Now I want to give generic read write permission, so for that I'll just write 0x c 1 2 3 4 5. Oh sorry, it's not x, c 1 2 3 1 2 3 4 5 6 7. Okay, so it means generic read write. Okay, after that I'll say no sharing, just I can give 0. Then I'll say default security attributes, say security attributes. In here I'll mention it like no sharing of resource. Then after that I'll say like just open the existing one. Okay, so open existing, then 0 comma this is means like no attributes. I'm going to pass attributes. After that I'll say no templates needs to, you know, mm, be embedded here externally, something like that. No template file. This is our handle. Okay, let's release this pieces. Okay, now if what if the handle not found, we need to write that code as well. If not handle, okay, or handle equals to -1 not found, then I just need to print handle not found, handle not found. Okay, means like if this path is wrong, then it should print like this. Okay, nothing magical here, just this dot exit with 0 code. Yeah, now yeah, this is it. And now what we're gonna do here, we need to see the size of the buffer. So if you remember, if we go here, okay, and if I go in ida, okay, I think, yep, load existing, reload file. Okay, if we open ida, if you remember, we can just open that file over here, and yeah, we can see, we'll say overwrite the existing data, whatever it is, because we haven't saved anything previously as well. So same stuff, we'll sort it by function name, and we'll see IRP device control, IO control handle, we'll change it to text view, and here we'll see our function buffer overflow stack IO IOCTL handler. Okay, that's it. Yeah, trigger buffer overflow, we can see, yeah, this is the size. Okay, so this size is in hex bytes. So if we want to see the actual, we need to convert this to decimal. So just copy 820, just go here and see the calculator. Okay, in here just paste it, hex 820. Okay, you can see 2080 is the decimal bytes. Okay, 2820 means 2080 bytes are there. So if we pass more than this data, it should give us like a blue screen of that. So let's check it out, like is it working or not. So we'll go in our code again. Okay, so what we'll go, we'll define like, okay, mm, another variable called bug equals to, we'll say bytes 41, x41 means a. Okay, you'll see a lot of a's. Okay, a, sorry, a 5000. I was writing, okay, so it should be more than this value. Okay, nothing, I just wrote 5000 just for that sake. So after that, I need to check the IOCTL code. Okay, so I have already found this from the memory from the IDA. It's 0x222003. Okay, I'll show you here as well. Yeah, yeah, you can see here here when uh, this value is actually the IOCTL, handle code. Okay, so we took this value here, so you just don't get confused on this one. So I think I told you earlier about this, yeah, CTL code. Okay, so IOCTL underscore code equals to this. Okay, after that we need to make the call to the device IO control. Okay, so we need to write another function, make the call to device IO control, and we have kernel 32 dot device IO control, and first handle comma, first we have handle, that is the handle to the device. Okay, okay, spelling mistake, handle to the device. Okay, then we have the IOCTL code. I'll say IOCTL code to trigger the vulnerability. Then we have the bug. After that, mm, okay, size more than the buffer. The buffer. After that, we'll say length of bug. Okay, then output buffer we don't need. Put buffer is none. Then I'll say buffer size, output buffer size is 0. Jai Shri Ram. Output buffer size. Then we will have the ref c u long. So yeah, this is the bytes return. Okay, and then after at last we have none, like we don't want any overlaps. Okay, lapped not needed. Okay, so if this ran right, we can't see any any message or something like that. We just gonna see the blue screen of that. But you can write, if you are writing an exploit for that sake, you have to write like print, okay, exploited successfully. That message should come, and that should pop you inside, pop you inside the admin shell. Okay. Exploit completed. Okay, So what I'm gonna do, I'll just copy this one. Okay, and I'll go to our debugging machine. I'll go to videos. I'll right click. I'll create new text file, exploit.py. Yeah, and I'll open it in Notepad. mm, I'll save it, close it, cmd over here. So if everything is fine over here, it should give us the blue screen of death. Python exploit.py handle not found. Okay, I think we need to check whether our handle is uh, on or not. Okay, sometimes yeah, start service. Yeah, now we just loaded the driver. So yep, I think that uh, that exception error message worked here. So yeah, it's a good thing. Then now we gonna exploit again by okay, uh kernel 32. Okay, did you mean that small spelling mistake? I'll do it here. Sorry. Okay, now it should work. Yep, exploit has been completed. Now you can see the blue screen of death and the system is restarting again. Okay, so cool. So you have learned so far like how you can crash a system with buffer overflow, but we don't need to crash the system. Okay, we need to actually you know spawn another shell with the higher privileges, or trigger and trigger a reverse shell to get the full access of the system, something like that attacker want to use. So for that you need to place that shell code just before just after the buffer overflow happens, which will eventually write your instruction pointer, and then after that you need to create one rope gadget which will trigger your shell or your malicious payload. Yeah, that's it. We're gonna continue that in the next tutorial. For now I think we had enough. Okay, so yeah, you can practice this. uh, there is a delay because I'm also occupied in so many work alongside. So whenever I get time, I create these videos for you guys, because I love to share this knowledge, because I also learned from the internet. Now it's my time, if I know something, to give to the internet. Thank you everyone. Have a great night. So it's yeah. Bye bye.